discuss about how to solve the PDE by using MSV. Okay. Now, before we going to proceed with another example, I'm going to introduce you some other method, which is the Alembert method here. Okay. So this Alembert method, all right. This Alembert method is used to solve, okay, wave equation for infinite boundaries. Okay, so we have how many types of PDE there that we have discussed earlier? We have what? We have heat, we have wave, we have Laplace, we have heat for 1D, 2D, 3D, right? But you have to take a look at the limit given also, okay? Where if the PDE given is wave equation for infinite boundaries, okay, or boundaries that are far away and does not influence the wavelength, such as this, okay? So this is the wave equation where it involves u, x, and t, and we have del squared u there, okay? Subject to the boundary condition, okay, you are given the boundary condition, ux0 equals to fx, and utx0 equals to gx. So u here, you differentiate with respect to t, and then substitute the value of t equals to 0. So sum equals to fx and then equals to gx for the derivative one. Then, by the Alembert method, okay, the solution will be given by this formula. So this is the formula of the Alembert method. So the Alembert method is quite easy compared to the MSV because we have this kind of formula. Okay, so now let's try to solve this example. Okay, so wave, this Alembert method is used for wave for infinite length, infinite boundaries. All right, so now let's take a look. Okay, by using Alembert, you have del squared u del t squared minus del squared u equals to 0. As you can see, if you rearrange in terms of this form, you can have what? Del squared u del t squared equals to del squared u del x squared, where we can see that c here equals to 1, right? Okay, so the given limit here ux0 equals to sine pi x del u del t x 0 equals to 0.5, where this is ut x0 equals to 0.5. Okay, so this is wave equation, all right? And we can use the Alembert to solve wave equation here. Okay, clear not? All right, guys, clear not? For this case, it is not mentioned about the limit, but this is the example used for the Alembert. So usually the limit is given. So as you can see, when the PDE is a wave equation and the limit is in terms of infinite boundaries, then you know that we can use the Alembert. Or sometimes it is mentioned that by using the Alembert method, you need to solve this kind of problem. Okay, so now how can we solve it? Okay, so you know that this is wave equation. You identify the value of C there. Okay. So now we have what? Ux0 and utx0. You know that ux0 is equals to fx, utx0 equals to gx. So your fx should be sine pi x. Okay. And then c equals to 1. So now we want to have fx plus ct, fx minus ct. So fx is sine pi x. So fx plus ct equals to fx plus t. Right, where c equals to 1. Sine pi x plus t. Alright, and then fx minus ct equals to fx minus t. Alright, equals to sine pi x minus t. Okay, and then your gx is what? What is your gx there? As you can see, gx equals to a function with utx0 there. So gx equals to 0.5 here. And we want to have what? We have fx plus ct, fx minus ct. Then we want to have gs. So if gx equals to 0.5, what is your gs? Anyone? If gx equals to 0.5, your gs is still 0.5, right? Because there is constant there. Okay? Constant doesn't change with a variable. Okay, so gx is 0.5, gs is 0.5. If your gx, let's say if your gx is 0.5x, only then you have gs 0.5s. So only change the variable. So if it is a constant, then just remain the value of constant there. Okay, so now you have all of the information. So just substitute to the given formula. So in order to find uxt, so you have 1 over 2 fx plus ct sine pi x plus t plus fx minus ct sine pi x minus t. Okay, plus 1 over 2 cc is 1 over 2 gs x plus ct is what? X plus x minus ct is x minus t. X plus ct is x plus t. Gs is 0.5. And then integrate with respect to s. Okay? So just solve this equation, this expression to get your uxt there. So now this is just an expression. So you just need to solve this part, right? Integrate. So integrate will give you what? Here. 0.5s x minus t x plus t. 0.5 x plus t minus 0.5 x minus t. Okay, will give you 1 over 2 t. Right? So just substitute your uxt equals to 1 over 2 sine pi x plus t minus plus sine pi x minus t, okay, plus 1 over 2 t. All right. Okay, up to this point, are we clear? So this is your uxt. Okay, and then by identity, you know that sin x plus y plus sin x minus y equals to 2 sin x cos y. Okay, so now we have 1 over 2 sin x plus y plus sin x minus y. So we can have 2 divided by 2 only sin pi x cos pi t plus 1 over 2 t. So this is your x, this is your y. So x is pi x, just expand this. Y is pi t. Then we have this as your u xt. All right, any question? Understand or not? All right, it's quite easy, right? Compared to the MSV, because we just use all of the information given, then just substitute to the formula. But this the Alembert is only applicable for wave equation of infinite. Okay? All right, if you have no question, why don't you try the next example there? The given answer is there, you just need to show. Example 4, show that the solution of the wave by using the Alembert is given by that uxt there. Okay, try it. After this, we discuss. Discuss. Okay, so now you know that this is wave. Okay, you know, first thing first, you have to know that this is wave equation. Okay, and then by D'Alembert, you need to identify what is your fx, right? What is your fx? From here, fx is equals to sine 2x. Okay, and then c there equals to 1, right? So fx plus ct equals to what? Fx minus ct equals to what? Okay, so here is sine 2x plus 2t. Okay, because sine 2x plus 1t, right? So we have sine 2x plus 2t. Then here, sine 2x minus t, sine 2x minus 2t. Okay? And then gx, what is your gx? Gx equals to sine x. So gs equals to sine s. Alright? Then just substitute. So uxt equals to 1 over 2 sine 2x plus 2t. Okay? Plus sine 2x minus 2t. Plus 1 over 2. 1 over 2 integrate x minus ct, x plus ct, gs. Right? Okay, so we have here integrate sign, you should have negative cos s, so x minus t, x plus t. So give you 1 over 2 all right, and then by using the identity, the same with the previous one, we have 2 sine x cos y equals to sine x plus y plus sine x minus y. Okay, and this one is for this one, sine and sine. Okay, and then we have cos here. So 2 sine x sine y equals to negative cos x plus y plus cos x minus y. So substitute here. So this is half. So just put this half divided by 2. And then we should have your uxt equals to sine 2x cos 2t plus sine x sine t. Because this is half and then this is 2. So you just, in order to have half here, then you just divide by 2. So that's why we only have 1 sine 2x cos 2t here and 1 sine x sine t here. Is that clear, everyone? Anyone has a question? Okay, so this is how you solve the wave equation, okay, by D'Alembert method. So if it is D'Alembert method, it's quite easy for you to do it, all right? Even though for MSU is quite long, but once you can do up until all cases, it is more than enough already. But you have to proceed with finding and fulfilling all the condition given, okay? Because based on my experience, the previous students somehow managed to solve up until case 3, and then there is not enough time. They just stop up until case 3. So the uxt is in terms of another constant, still has a constant value. But don't worry, okay, the marks is quite high up to that point. But if you have enough time, you just can proceed with solving and using all the condition given. Okay, so that one is for MSV. But for the Alembert, it's quite easy. Then just use it. So apply the formula there. Okay, just understand the function of fx and gx. Okay, even though you don't know how to use the identity you solve up until here. Okay, I'm not saying that this is wrong, but maybe you will deduct about 2 marks, 2 to 3 marks like that. Okay, so don't worry. As long as you know how to use and you know how to solve, then you may proceed. Okay, is that clear, everyone? Any question? There. All right, so previously we have discussed on how can we solve a heat equation, right? Heat equation by MSV method. Okay, and then for that heat equation, we have mixed endpoint, zero endpoint, insulated endpoints. And I have discussed with you of zero endpoints and insulated endpoints, right? So zero endpoints only involve with U, okay? Here, U only. And then mixed and insulated endpoints involve with Ux. So you just differentiate U with respect to X, okay? So for mixed endpoints, it is just a usage of U and also Ux. Okay, so it's quite same process with the either for zero endpoint and also for insulated endpoint. So there is no example for heat equation for that. Okay, and then now for wave equation for infinite boundaries, we use the Alembert method, and also we can use MSV to solve wave equation. Okay, so let's discuss how can we solve wave equation by using MSV. Still MSV, right? But for this MSV of wave equation here, okay, it is used for the finite limit there. Okay, for the infinite, we use the Alembert. Okay, so how can we solve by MSV? Same process with the previous one that we did. So as you can see here, we have a boundary condition U and U. This is zero endpoints. And the initial condition U and UT. So here we have a mixed endpoints. All right. So even though heat equation doesn't discuss this, now we have wave equation and the process is similar. Okay, so where should we start here? We have this example. Use the MSV method to find the solution. Okay, where we have the boundary condition and the initial condition there. All right, so how can we find this? Okay, how can we start? This is PDE and we are going to use MSV. So where we should start with? What is our first step here? Come on. Yes, we have to reduce PDE to ODE. Okay, but before you reduce, you need to have your expected solution. What is your expected solution here? Wave equation here involve U, X, and T. So first, you need to reduce PDE to ODE. So before you reduce, you need to identify what is your expected solution. For this case, you have to have what? U in terms of X and T. Okay? Okay, so you have U, you have X, and you have T there. So the expected solution is U equals to XT. So now you match with the PDE given, where this PDE need to have U double T, right? And U double X. So your U double T should be XT double prime, U double X should be X double prime T. And then substitute. So you have here del squared U del T squared. So this one is UTT for UXX. So UTT is XT double prime for X double prime T, right? So rearrange, you have X double prime over X equals to T double prime over 4T. And then these two are equal when there exists a constant of lambda. So we just can separate. So we are going to have X double prime minus lambda X equals to 0. T double prime minus 4 lambda T equals to 0. So this is your ODE. Okay. All right. What is the boundary condition? Okay. Second step. All right. I'm not going to give everything here. So let's do this together. This is just the same process. What is the ODEs here? The boundary condition. So this one only. Okay. So what should we have? All right, x0 equals to 0, x2 equals to 0. Okay. Then you need to consider all cases. So I'm going to leave you with this example as the activity. So please submit the activity later on the e-learning. All right? Are we good? Okay. So same process. All right, same process with the previous one, but here we have wave equation. All right, so I'm going to leave you here, and if you have question after this, you can ask. Okay, so that's it. So we have done discuss with the Alembert. You may try the past year question of the Alembert also. Okay, and then don't forget to scan your attendance here. Okay, guys. Let's end our class with Suratul As and Tasbih Kifarah. Thank you, everyone. Assalamualaikum.
Thank you, Dr.